So good afternoon, everyone. Welcome to this edition of the NITheCS Colloquium. My name is Francesco Petruccione, and today we are very fortunate to welcome Professor Matthew Bales from Australia to be with us. As you probably know, Cape Town is hosting this week one of the biggest astronomy and astrophysics event, the International Astronomy Union annual event. It's the first time that it is held in Africa, so it's really a big thing. There are several thousands of people and participants, and we were lucky, thanks to Professor Ying Shema, to convince Professor Bales to do the little detour to Stellenbosch to give us a colloquium. Yeah? I will ask now Professor Ying Shema, who knows Professor Bales much better than I do, to briefly introduce him.
Thank you, Francesco, and hello, everyone. It's my great honor to introduce Professor Matthew Bales, my friend for many years. So he is an expert in discovery of the pulsars and fast radio bursts, and currently leads the MeerKAT key science projects on South Africa's remarkable MeerKAT telescope. And Bales was awarded the PhD at the Australian National University and completed postdoc research at NASA and also University of Manchester in the UK, and also Australia's Commonwealth Scientific and Industrial Research Organization, CSIRO, and the University of Melbourne in Australia before founding the Swinburne University University of Technology Center for Astrophysics and Supercomputing. He's known for his many discoveries of the millisecond pulsars and their use in the tests of the Einstein theory of relativity. And in 2007, he was part of the team that discovered the first fast radio burst, FRB, that was awarded the Shaw Prize in 2023 in recognizing that. Shaw Prize is named for Ran Shaw, the Hong Kong business and also philanthropic for education and so on. And he has a passion for public outreach and was developed some remarkable virtual reality tool for demonstrating the remarkable phenomena that take place in our universe that I used to show explicitly to the public lecture. I believe he will use some of them today.
Thank you very much, Yingche. Professor Bales, the floor is all yours. Thank you very much.
Thanks very much. It's nice to be in Stellenbosch. I'm actually a distant relative of Barai, who has a statue in the park here. So it's nice to come and visit my cousin. My ancestors founded some of the wineries in the area, and I've been fortunate to come back to Stellenbosch many times. But this is only the second time I realized I was actually related to anybody here. So I'm going to give a talk about a virtual tour of Einstein's universe. Hopefully I'll be able to show my slides at some point. And I'm going to use something called Osgrad's Virtual Universe, which is actually a computer game designed to teach astronomy. So you are my pupils. We're currently orbiting Mars, and we're actually orbiting the moon, which is called Phobos, and looking at Mars. You can see Phobos is coming into view. Right-hand side, it's kind of dark. Let's just move it across a bit. So Phobos, unlike our moon, is not very round. And that's because it's only about 10 kilometers in diameter. And so it doesn't have enough mass to squeeze everything down to a sphere. So this talk is really about gravity, and our understanding of gravity has changed over the course of many years. On the Earth, the tallest mountain is only about 8 kilometers high. That's Mount Everest. On Mars, which is what we're looking at here, the mountains are much higher because gravity is so much weaker. So Mars is only about 1/3 of the mass of the Earth, but the volcanoes are much larger. And in fact, they fly in here and take a look at them. And if you tilt it on the horizon there, you can see Olympus Mons is on the left. It's actually 27 kilometers above what you might think of as sea level. And there's the other volcanoes. And the reason these haven't fallen down is gravity is just so much weaker on Mars. so it can't compress them much. There's also very little atmosphere on Mars. The atmosphere is only about 3% of the density of the Earth's atmosphere. So although Mars has very strong winds, their eroding qualities are not as high as they are on the Earth. So we're very familiar with our own planet, Earth. I'm actually from a little town called Alice Springs, which we fly in here. Is right near where my cursor is. And I was born there back in 1963, but I currently live in Melbourne, which is on Port Phillip Bay, down the bottom here. And the radius of the Earth is actually 40,000, or sorry, is the circumference of the Earth is 40,000 kilometers. And that's because the meter was defined by the French, so that there would be 10,000 kilometers from the North Pole to the equator. Now, in this talk, we're going to not just tour our own Earth and solar system, but also places that have been discovered by radio telescopes around the world, and learn about how gravity works on different scales. But before we do that, let's just fly over and have a quick look at some of the planets. So the closest planet to the Sun is Mercury. Mercury looks a little bit like our moon. It's only about 5% of the mass of the Earth, and it has no atmosphere. It also rotates very, very slowly. So it goes around the Sun about every 3 months, but it only spins on its axis about every 66 days. And it gets extremely hot on the sunny side and extremely cold on the other side. We go to Venus now. Venus is about the same mass of the Earth. It doesn't have any moons, and it has this very thick atmosphere, and it's like the ultimate CO2 furnace. It's so hot that it actually rains sulfuric acid, and every spacecraft we've ever sent to Venus has not lasted very long because of the corrosive nature of the rain there. We go to Mars. Mars has 2 moons. The first of those moons is Phobos. And as I said before, Phobos is not very round, but it's only 10 kilometers across. There's another moon, Deimos, and we can actually look at Mars from these moons. And if I speed up time a little bit and turn on some traces, we actually must be going Phobos. Let's go to Deimos. If I speed up time, you can actually see how Phobos goes around Mars very, very quickly. And in fact, the orbital period of Phobos is much less than the rotation period of Mars. So Phobos rises in the west and sets in the east. It actually goes around Mars about 6 times for every once that Mars rotates. Going further afield now, Jupiter is a large gaseous planet. Its density is only about 2 grams per cubic centimeter, and it spins very rapidly. It actually spins around every 9 hours, and it has this very long duration storm, which is the Great Red Spot, which has actually been known about for hundreds of years. Jupiter has its own little solar system of moons. It has 4 major moons, but about 70 minor moons. And these moons travel around from about once a week to once every few weeks. Next up is Saturn, which has these spectacular rings. And we can actually fly out here. And you can see that Saturn actually casts its shadow on the rings. We rarely see that shadow because we're so close to the sun that we just see the sunny side of Saturn. If you fly a space probe past Saturn, you not only see the the rings being shadowed, but also the fact that the rings cast a shadow on the surface of Saturn. And then there's the relatively boring Uranus and Neptune, and Pluto's been demoted from no longer being a planet. But it was partly because of the way it was formed and its rather tiny mass. So the stars have been very important for science. They were a great aid to navigation. They also taught people on Earth when the seasons were changing, when the different stars would rise and set. And the Greeks had a different name for the planets than the stars and knew that they were special. So if we actually look at something like Jupiter from the Earth, if I speed up time, you'll see that planet means wanderer in Greek. And so the planets used to wander against the fixed constellation of the stars. And if we speed up time fast enough, you'll see that indeed Jupiter travels throughout the night sky, as does Saturn. And this was recognized by the Greeks many years ago. And they also noticed that the trajectory of the planets was not regular. They didn't just travel in a very uniform way. What we're actually going to see in a minute is the principle of retrograding, where Jupiter and Saturn appear to stall and then travel backwards, curiously for about 6 months, and then take off again. And this was explained by the ancient Greek astronomers as having something called an epicycle. They knew that the planets moved in roughly a regular pattern, but every now and then would turn around and go backwards. And this led to a very confused universal model where the Earth was at the center of the universe and the planets did these funny wiggles. And we now understand that is because the Earth isn't actually at the center of the solar system. Although various scientists were attributed the fact that maybe the Earth wasn't at the center of the solar system throughout history, the first person to recognize it and argue for it strongly was Copernicus, who was a Polish astronomer in the 1500s, but he was so terrified that if he published his theory that the planets went around the sun instead of the planets going around the Earth, that he only actually published his theory the year of his death and didn't get to see that it was widely recognized. So we can fly to the sun. Sun spins around about once a month. And if I pull out the Copernican model of the solar system can be seen operating here. We've got Mercury goes around the sun about every 99 days. Venus a couple of hundred, the Earth 365, Mars somewhat slower, and the closer you are to the sun, the faster you travel. And then if we pull out, you can keep seeing that the scales in the universe are so vast that in order to see Mercury going around the sun, the outer planets appear to be almost not moving. But if I speed up time fast enough, you'll see there's this wonderful orrery-like behavior going on the inner planets. Jupiter takes about 11 years to go around the sun and Saturn about 30. So this was the Copernican model of the solar system. And it wasn't properly explained until the time of Kepler. So Kepler was, again, a Polish astronomer who visited Tycho Brahe, who was the world's greatest optical astronomer. And he'd carefully worked out the locations of the planets over the course of many years. And Kepler took that data and came up with his famous laws of motion. And that was that Um, so Kepler had three laws of planetary motion. The first was the planets moved in ellipses with the sun at one focus. They swept out equal area and equal time, and that, let's grab my laser pointer. Whoops. There we go. Wrong button. So one was that the planets move in ellipses with the sun at a focus. What do I mean by an ellipse? An ellipse, what happens if you get a piece of string, indicated here by the blue, and you nail down the ends and you make it taut. And then if you trace out a shape, that's actually the shape of an ellipse. And according to Kepler, the sun was at the focus of an ellipse, and the planets traveled around in an elliptical path, and the speed at which they traveled depended on how close they were to the sun. So they swept out an equal area and equal time. And if I turn on the elliptical path here, you'll see that the planet travels more slowly when it's a long way from the sun than it does when it's near the focus. And so this was Kepler's second law. He published that in 1610. And then in about 1619, he came up with the fact that the orbital period, how long it takes you to go around, depends on the 3/2 power of the semi-major axis of the ellipse. He didn't know about Newton's constant, that sort of thing, but we'll learn about that in a minute. We want to see that in a bit more detail. Here we've got the motion of the planet. The sun just sits at the focus, and you can see it going much closer when it's near to the sun than far away. And in Kepler's theory, the orbits were in a plane, which is akin to what we believe is currently the case. So if we want to see how that works in our solar model, spinning, speed up time. So every second of our time is 1.2 days in this model. And you can see that Mercury is actually in an elliptical orbit. Speed up a fraction more. Whoops. You'll see that Mercury's orbit is actually elliptical in shape. It's closer to the sun over here than it is over here. Venus and Earth are much more circular in their orbit. The Earth's position with respect to the sun changes by about 1.5%. We're lucky it doesn't change by much more than that. It would get rather hot and cold at different times of the year. So in Kepler's laws, he could explain not only the fact that the shapes were correct, but also the time it took the planets to go around depended on this 3/2 power of the orbital distance. So we go to the next slide. Newton came along in 1666 and he came up with his universal law of gravitation. We were very lucky that there was the Great Plague of London in 1666 and Newton was sent home. And while he was home for a couple of years without people bothering him, he worked out the universal law of gravitation and also differential and integral calculus, which was a very good sabbatical. So in Newton's theory, objects of mass m accelerate if a force is applied. And Newton realized that the same force of gravity that made apples fall from trees could explain the motion of the moon around the Earth. And so he came up with this theory where he had Newton's cannon. And the idea was that if the cannonball just rolled out of the cannon above the Earth, then the moon would just fall into the Earth. So let's see how that works. So the moon just splashes down due to a problem in my program, it shoots out the other side. It wouldn't really happen. If we instead give the moon a little bit more power, it tries to get around the Earth, but it falls down. If we fire it a bit faster, and we get it to the point where it falls at the same rate as the Earth is curving, it would actually be able to make it in orbit, but it doesn't. It's going to emerge out the other side of the sun soon. So let's just spin around and see the moon splash down. So it hasn't been given quite enough speed, so it's going to plunge into Africa or something. Luckily, it missed Cape Town or Stellenbosch. And then, if on the other hand the cannon was too powerful, then the moon would escape the Earth's gravity and almost take us out. But if we get the speed exactly right, then the moon will fall at exactly the same rate as the Earth curves, and it will just go into an orbit forever. And so this is how Newton explained the orbit of the Earth. So I can actually trace the orbit, and you can see that it's a nice circular thing. I'll just get our perspective right. And you can see here that the moon is falling, and according to Newton, it's being attracted to the Earth, but it wants to go in a straight line, but it's accelerating because of the force, and it just keeps going around the Earth forever. Now, the moon isn't actually this close to the Earth, which is rather lucky, because otherwise the tidal forces would be rather extreme. But we can look at a real scale model, and you have to spot the Earth and moon here. That's the Earth there, and this is the moon. So this is more like the real scale. But for illustrative purposes, it's much nicer to be able to put in a trajectory that the moon is under. And so this is why the moon travels around the Earth according to Newton. And in fact, Newton showed that if you take his equations back here, if you do a little bit of calculus with this force and the fact that force equals ma, you can actually derive all of Kepler's laws. They're just a natural consequence of universal gravitation and force equals ma. And there used to be a thing back in the 1970s when I was a boy. There was a commercial for Colgate toothpaste, and they used to appeal to women's insecurity by saying, if you use Colgate, you'll have the Colgate ring of confidence. And so in this, the Earth appears to have a Colgate ring of confidence as well. Just a bit of history there for you. So we didn't get a lot of progress on understanding gravity until Einstein came along. And Einstein realized that if you were in an elevator with no windows and you were on the surface of the Earth, you would feel gravity. But if you were being accelerated at the same 9.8 meters per second squared by a cable, if you were inside the elevator, you wouldn't be able to do an experiment that would tell the difference between these two circumstances. So if you're doing a physics experiment in here, you feel just like you're being accelerated in outer space. And so he thought maybe gravity and acceleration are actually equivalent, and he came up with his general theory of relativity. So in Einstein's theory of relativity, if you're in an elevator that's free falling, you can't tell the difference between free falling in a gravitational field and having no acceleration in outer space. And there's some consequences of that. And one is that light should bend around bodies. Because you could imagine if you're in here with a mirror and you are bouncing light between the mirrors, but falling, the light must bend as well. According to Einstein, clocks should tick more slowly near a gravitational body than in outer space. And space should actually be compressed near a black hole. In fact, if you had a ruler and you took it near to a heavy object, I haven't told you what a black hole is yet, but black hole is something that's got infinitely dense. then rulers should be much smaller nearer a gravitational object than far away. And in fact, he worked out that if the radius of an object was ever, according to this formula, light couldn't even escape it. And so to make the Earth into a black hole, we'd have to compress it so it had a radius of 9 millimeters, about 1 centimeter. And to make the sun into a black hole, we'd have to squeeze all of the material into something only 3 kilometers in radius. So this all seemed a bit of a fantasy because it's actually pretty hard to get even a liter of water and condense it down to 1 millimeter. He also showed that if there was an analogy between electromagnetism, which is the theory of light, and gravity, then when two bodies went past each other, they should emit something called a gravitational wave. And this wave would take away energy. If you wanted to try and detect a gravitational wave, it would be quite difficult. Gravitational waves, as they travel through space and time, they cause matter to stretch and squeeze. And you can work out something called little h, which is the factor that you're compressed by. And it's by this formula. And if you do this formula for the Earth and the Moon, you would see that h would be about 10 to the minus 24, which is a very tiny amount. Such a wave, you would need an apparatus that would have to be about a light month and be about 3 million kilometers. So here's that calculation. So if you could get a 1 million kilometer ruler, it would shrink by 1.4 by 10 to the 15 meters, which is about the radius of a proton. So Einstein thought this was pretty hopeless and that gravitational waves would never be detected by anybody. But you could do other tests of Einstein's theory of relativity. The fact that gravity travels at the speed of light means that you're not actually being attracted towards the sun when you're going around it. You're being attracted to where the sun used to be. And so Einstein worked out that according to general relativity, the elliptical orbit of Mercury should precess by 43 arc seconds a century. This is 1 degree every 8,400 years. And although this doesn't seem very much, it was actually known about in Einstein's time, and it was considered the first test of general relativity. Let's just quickly see how that works. So there's Mercury's orbit. And if we speed up time, this point of closest approach to the sun, every 100 years changes by 43 arc seconds. And an arc second is 1/3600th of a degree. So it's actually less than the radius of Mercury per orbit. And yet astronomers knew about it back in the early 1900s. And so this ellipse every 8,400 years will advance by 1 degree, or I think it takes about 1 million years for it to complete a complete cycle, which is not a particularly interesting number. Another test of relativity was to look at the sun during a solar eclipse. And here's a solar eclipse here. Pause time. Oh, move it back. So if you wait until the moon blocks the sun, which I did, the stars behind it actually have their position apparently changing because the light bends by a couple of arc seconds. And so Eddington in 1919 went to a location where the sun was going to be eclipsed, and they took this is a negative image of the sun being eclipsed. They measured all the positions of the stars around near the sun during the eclipse, and indeed they'd moved by this amount, which was another proof, if you like, of Einstein's theory of relativity. And then it had to wait until the 1950s when we developed atomic clocks that people put an atomic clock in an aeroplane. They flew it up 10 kilometers above the Earth's surface, the clock ticked faster because it was out a little bit out of Earth's gravity. When they landed it, they compared its time to an atomic clock that had stayed on the Earth, and indeed it had clicked faster by the amount that Einstein had predicted. And indeed, GPS, the modern global positioning system, uses these Einsteinian corrections. Otherwise, the clocks don't tick at the right rate. So Einstein's predictions can be listed here. Clocks should tick more slowly. That was checked. There should be waves of gravity removing energy from pairs of stars in orbit. That was not checked. Rulers should shrink. Black holes should emit no light, but black holes seem to be a theoretical impossibility. Spinning objects should drag space and time around them. Light should bend around bodies. That was done by the eclipse test. And the spins of an orbiting star and an orbit should actually couple and precess. And finally, gravity should travel at the speed of light, and that's why these Mercury's orbit precessed. So in terms of detecting gravitational waves, Einstein thought this was hopeless, because when in his time, the only stars we knew about were stars like the sun. And so you can actually work out the minimum orbital period around any body, and it just depends on its 3 pi at big G, which is Einstein's constant, and the density of the object. And if you work this out, then the shortest period in the universe should be a few hours. And that's because the density of the sun is only 1.4 grams per cubic centimeter. And normally stars are like hundreds of radii apart. And so if you want to actually measure gravitational waves doing normal stars, that's pretty hopeless. If you look at Jupiter, things aren't much better. It has about the same density of the sun. That's because it's made up of the same stuff. If you look at the Earth, we're a rocky planet, so our density is a little bit higher. And the orbital period of something just near the surface of the Earth is about 90 minutes. But again, that's not very interesting from a gravitational test theory. And if you look at how big the Earth is compared to the other planets, whoops, how am I going to do this? Some magic button I can press. Nope. Yeah. There we go. That would be the Earth compared to the other planets. So there's Saturn with not even a ring width. Those little guys next to the Earth are the Moon and Mars. And then if we pull out a bit, we can see how tiny the Earth is compared to the Sun. It's only about 1% of the radius. Because of that, you can fit 1 million Earths inside the Sun. So in Einstein's time, he only knew about stars like the Sun and planets like the solar system. And if you worked out the amount of gravitational waves the Earth gives off going around the Sun, it's just meaningless. Luckily for us, the Sun is not a particularly big star by the scale of the solar system. So this is the Sun. This is a star called Rigel. You can actually see this from the Southern Hemisphere. And the only reason the Sun looks comparable is because we're kind of close to it. We zoom out a bit. You can see that the Sun, which is just here, is actually really tiny compared to Rigel. Rigel is about 20 times the mass of our Sun. Its mass is known quite accurately, as is its radius. It's about 4 times hotter, but its luminosity, how much energy it's giving off, is 100,000 times that of the Sun. We know its distance because of the Gaia satellite to just a few light years, and it only lived for about 10 million years. Our Sun will live for about 10,000 million years. And Rigel will blow up as a supernova and leave something called a neutron star behind at the end of its life. And this is a star that blew up in 1054 AD. It's called the Crab Nebula. Looks a bit like a crab, according to some people. And in the center of that, there's a neutron star, which actually is lighting up this object. On the right here is what the sun is going to look like when it dies. It will leave behind a little sort of burnt ashes called a white dwarf and this beautiful, what's called a planetary nebula. We live in a galaxy that looks a little bit like this. This is the Andromeda galaxy. It's a spiral galaxy. They kind of flatten one direction and have these spiral arms. And we think we're about 2/3 of the way out from the center. And this is a animator's impression of what the Milky Way looks like. It's got a central bulge. It's got a bar. It's got these spiral arms. And it's very, very thin. So the place where the stars are made is remarkably thin. And that's because gravity makes spheres compress and rotation makes them avoid collapsing to a dot. And so we think we're about 2/3 of the way out from the center of our galaxy. And there's about 400 million stars in our galaxy, many of which blow up about every 100 years or so. If you use a radio telescope to look at the sky, instead of seeing stars, you see hot gases. And these things here are actually, they're called supernova remnants. And down here is actually a supermassive black hole squirting out jets of emission. In the middle here is the galactic center. And right in the guts of that is a 4 million solar mass black hole. And that's a very active region of our galaxy. We're lucky enough in South Africa to have this wonderful MeerKAT radio telescope, and it made that image of the sky. And this was used at the grand opening. I used that telescope a lot, but I was trained on the Parkes radio telescope in my native land. And the Parkes telescopes discovered about half of the pulsars in the known sky. So in the 1960s, there were these mysterious things called quasars, and quasars didn't, or twinkled in the night sky, but radio galaxies didn't. And this is a model of a quasar. It's a supermassive black hole with a disk of material. The disk is magnetized and it squirts out these jets, and that's what you can see here in the image. A student called Jocelyn Bell had a PhD to study quasars and how they twinkled, and she and her supervisor built this radio telescope in Cambridge, and they had a very new thing they were doing, was that they had a very short time constant on the radio telescope, so they could see changes in the flux of a source on very short time scales. And most radio telescopes just knew that nothing was changing in the universe, so they had an integrating circuit, which this one didn't. And lo and behold, because of that, she discovered what was called pulsars. So these were her chart records. They don't use computers to measure things. It used pen and ink. And the paper used to run under the pen. And when a source came on, the chart would go up. And then when it went away, it would go down. And she realized that this pattern was repeating with a delay of about 4 minutes per day. Well, it was coming 4 minutes earlier every day. And that's the rate at which this Earth spins with respect to the stars. And so one night they went crazy with paper and they did a very high trace rate. And you could see that there were these little depressions here. And this is actually the discovery of the first pulsar. So it's actually 1.33 seconds between these pulses. And she discovered the first radio pulsar. She soon found another 3. So this is what we think they kind of look like. They're a neutron star. They're only about 20 kilometers in diameter. They're very highly magnetized, and they have this beam of emission which shines throughout the universe. And if you're very lucky, that beam points at your radio telescope, and every time it sweeps by you, you get a pulse of emission. And that's what Jocelyn saw on her chart record. And her pulsar was rotating once every 1.33 seconds. A neutron star is about 500,000 Earth masses, and 1 teaspoon of a neutron star weighs about the same as all of humanity put together. So they're incredibly dense. And the reason they're so dense is there's no interatomic spacing. All the electrons have been combined with protons to form neutrons, and so you end up with these super dense, super magnetized stars. The magnetic fields range from about 10 to the 8 to 10 to the 14 Gauss, and for reference, a fridge magnet is about 100 Gauss. It turns out if you spin a magnet, it doesn't like it. It kind of screams, gives off magnetic dipole radiation, and a very tiny fraction of the energy comes out in radio waves, and that's what we see. So almost all of the pulsars we know about are in our galaxy, and they're only about 3 times bigger than the black hole a black hole would be. So if you could compress it by just another factor of 3, it would collapse to be a black hole. So there is a neutron star right in the middle of this remnant that was seen to explode by Chinese astronomers back in 1054 AD, and it rotates 33 times a second. It actually gives off about 1,000,000 times as much energy as the sun, and that's why this nebula glows. How big are neutron stars? Well, I've already said about 20 kilometers, but there's other ways that stars can end their lives. Very large stars become black holes, which are about 30 times the mass of the sun. Neutron stars are about 1.5 times the mass of the sun, and white dwarfs are about 60% of the mass of the sun. The white dwarf is about the same size as the Earth. And we're going to see all 3 of these objects later in the talk. So we're lucky that when radio waves travel through the universe, they travel at different speeds depending on how many electrons they've gone past. And we can use the delay of a pulse to tell how many electrons there are between us and the pulsar. And by having a model of the galaxy and how electrons are distributed in that, we can work out how far away pulsars are. And this is a map of where all the neutron stars we know of are in the universe. They're basically all in our galaxy. There's a little clump of them somewhere in our nearest neighbor galaxy. You might be able to see. Maybe we've got time later, we can have a hunt for them. But basically the sun is at the center of this clump of pulsars. And the only reason the sun knows to be at the center of all these pulsars is what's called a selection effect. It's easy to find pulsars near you. It's quite hard to find them on the other side of the galaxy. So it looks like the pulsars are clustered around the sun. But not really. There's just so many pulsars in the rest of the galaxy. We just can't find them because our telescopes aren't big enough. In the 70s, they didn't find pulsars with pen and paper. They used computers. And Russell Hulse and Joe Taylor discovered something called the binary pulsar. And this was a very exotic system. It was a neutron star going around another neutron star. And instead of taking like a year to go around each other, they actually went around each other every 8 hours. And because of this, we finally had a fantastic laboratory for doing gravitational physics. And the people who discovered this object won the Nobel Prize in Physics back in 1993. So how do you get 2 neutron stars together? We start off with 2 stars, a big star and a little star. The big star actually ends its life faster than the little star. And it actually swells up at the end of its life and transfers material onto the little star, and they actually have a role reversal. So this star becomes the biggest, and this is now the smallest. But this star here has run out of hydrogen, and it blows up. And when it blows up, it leaves behind a neutron star. Now, most of these systems disrupt at this point, and the neutron star just travels off into space. But if we're very lucky, the neutron star stays bound. I'm going to come back in a second. And you end up with a neutron star going around another star. And there's 2 examples of this that were discovered by the Parkes telescope. One is called 1259-63, Another one's called 0045. This is just where they are in the sky, deep in the southern hemisphere. And again, have these elliptical orbits that the systems are exhibiting. And I think I can zoom out. So basically, Kepler's laws still apply to all systems in the universe because of the universal law of gravitation. So you get a nice big elliptical orbit. The orbital period is typically many, many weeks or many, many years. And I've got a scale model. So the neutron star wouldn't be this big. It would just be a dot. You wouldn't be able to see it, but it wouldn't be much of a talk. So this is the dimension of the orbit of this pulsar 0045. We've been observing this with MeerKAT. It goes around its companion every 51 days. And for scale, that would be how big the sun is, that little dot. So it's a really gigantic orbit. After a while, the second star swells up to end its life, and material flows from the star to the neutron star. It forms what's called an accretion disk, and a huge amount of energy is liberated when the material falls onto the neutron star, because the gravity on a neutron star is about 1 trillion times stronger than that of the Earth. And in fact, it gives off so much energy, it's equivalent to 10 to the 5th nuclear wars per meter squared per second. And yet it doesn't destroy it. Like, these are hardy things. So these are what's called high mass X-ray binaries. Eventually, the transfer stops. You get a circular orbit with a pulsar that's been spun up by the accretion disk and a star that's about to blow up. Sometimes they don't blow up, however, and you get these very boring things called, oh, they're not that boring, millisecond pulsars. These can spin up to 700 times a second, and they have these little inert white dwarfs going around them in very circular orbits. This is a real example of one we observe with MeerKAT about every 2 weeks. Just turn on the trail. So these two guys go around in a circular orbit. The orbital period is 7.8051349696117 days. So we can measure it that accurately. The velocity in orbit's about 50 kilometers per second, and we know the distance quite accurately. The rotation period of the pulsar is 16.4529299728 milliseconds. And this is a real system. Amazing. There's another system which has the lightest companion, 1719 minus 1438. And this one, the companion is only about the mass of Jupiter. And it goes around the neutron star every 2 hours. And the whole system would almost fit inside the sun. And then finally, we have 1909, which is one of my favorite pulsars. It also has a ridiculously accurately known period. Its velocity is 200 kilometers a second. And this is one of the most important pulsars that we observe because it's such an accurate clock. In fact, we can use measurements of the system by turn on its orbit to test relativity. So in this system, the orbit is incredibly circular. And it's actually a very edge-on orbit. So we're looking at it face-on. But in the system, what's actually happening is the neutron star is very close to edge-on. And what happens is, when the light travels past the white dwarf, according to Einstein, the measuring rods should shrink. So it should take longer for the light to reach us than when the object is on the other side of the orbit. So we should get this time delay, and we can use that time delay to test the general theory of relativity, which we do. So these are our measurements, these little splodges, and the line is Einstein's prediction of how space and time should be compressed if he was correct. It's a bit of a shame he didn't live to see this. But if you take the model away from the data, these are what's called our residuals. And if Einstein's right, these should cluster around 0. And they do remarkably well. Another thing that's amazing about this orbit is that it's such a perfect circle that the difference between the semi-major axis and the semi-minor axis of the orbit is 4 microns. Even though A is 569,000 kilometers, and this thing is 3,500 light years away. We can measure it. Amazing. And then finally, if the second star blows up, you end up with what's called a double pulsar. So you get 2 neutron stars going around each other. Because of gravitational wave emission, in about 300 million years, those 2 neutron stars are going around each other so fast that their orbital period is 1 millisecond. They do 1,000 orbits every second. And they give off so much gravitational radiation, they rip each other apart, and you should end up with something called a kilonova. And then once they've merged, you have a black hole. So the binary pulsar that was the discovery of which was awarded the Nobel Prize in 1993 has an advance of periastron, or perihelion, I want to call it that. Just put on the orbit here. So that point of closest approach, instead of doing 1 degree of precession every 8,400 years, it actually does 4 degrees a year. And because of that, all of the gravitational effects in this system are amplified, and you can use it to tell how massive the 2 stars are. So we recall that Einstein predicted these gravitational waves, things should be happening, they should take away energy, and the orbit should shrink. And if you calculate how much it should shrink, it's 3.1 millimeters in orbit. So even though these things, 5,000 parsecs, or about light years away, the fact that they're shrinking so regularly means that over the course of about a decade, the pulsars get back closer together a few seconds before they would if there were no gravitational waves. So this is Einstein reached the periastron position, and the dots are the points. And in 1993, they were awarded the Nobel Prize. And who wouldn't? You got the Nobel Prize. You don't need anything. Started observing again. So this is the relativistic, which should, or how the pulsars should get back together again. And that's was why the Nobel Prize was awarded, because they'd proved that gravitational waves exist. And because of that, we realized that if you could monitor 1 million galaxies for about a year, you should actually see neutron stars merge, and a wave of gravitational waves should travel through the universe. So they built something called advanced LIGO, 4-kilometer vacuum tubes. A James Bond style laser is fired into this thing. Half the light goes this way, half the light goes that way. It bounces off a mirror. The mirrors are set up so they're exactly half a wavelength apart. So when the light is recombined, you should get no light. And then if a gravitational wave goes past, the system will shake and you should see light. And so $500 million later, they'd built 2 of these systems, one in Louisiana. Here's one in Hanford, and here's Matthew Bales in Hanford on the advisory committee. And so there was a laser beam going down here for 4 kilometers, just hoping that neutron stars merge and the mirrors shake. And lo and behold, on the 17th of August, 2017, so almost exactly 7 years ago, they measured the gravitational wave frequency versus time in the detector. And you can see there's this beautiful sort of sweep. And this is the 2 neutron stars going around each other faster and faster and rip each other apart. And then 1.7 seconds later, there was a burst of gamma rays that hit the Earth. And they realized that this patch of sky here in green, there should be a new star appear there. And so they looked at it, and lo and behold, there was a new star where there didn't used to be one. And this was what's called a kilonova. And this is powered by a whole lot of neutrons, or a whole lot of atoms decaying because they've been formed from pure neutrons. And this is how you make gold in the universe. And so this was actually a proof that the speed of light from gamma rays and the speed of gravity from gravitational waves was very, very similar, because this system occurred in a place 120 million years, or 120 million light years away. And so the gravitational wave arrived just slightly earlier than the gamma rays did. So this proved the speed of light and the speed of gravity were about the same. How am I doing for time? Excellent. So this is that object 1909 minus 3744 I was praising before. It's so good because it has a very narrow pulse. This is the energy from the pulsar as it travels past our telescope. It's only about 40 microseconds across. You can get a typical signal to noise ratio of a few thousand with MeerKAT. And so every time we look at this thing, we get the arrival time to about 40 nanoseconds. And so by working out when these pulses hit our telescope, we can do some very cool things. And this can be applied to various systems, one of which is called the double pulsar. This is a system which has two pulsars going around each other, and these actually go around each other every 2.4 hours. They're in an eccentric orbit, and we've witnessed 3,948,400,142 rotations of this pulsar over the course of the last few years. And so what we're actually doing is mapping the distance between us and this fast pulsar on several dozen occasions, and we map the entire orbit. And what we can do is we can see if space-time is compressed when the light from one neutron star goes past the other one. And indeed, this is the Einstein prediction in red, and this is our data. If we subtract off the model of the motion of the system, we get what's called timing residuals. So every observation is accurate to a few tens of microseconds. And we have 30,000 observations of this thing, which is amazing. And this is the model, or the data minus the model, which is centered around 0. If I say that clocks don't tick more slowly when they're near each other, this is the residual as a function of orbital phase. And Einstein predicted that this thing should have an amplitude of 384 microseconds, and it's exactly what we see. We've also seen that this orbit is also decaying due to the gravitational wave emission. And in fact, the orbit shrinks by 2.7 millimeters in orbit. We've verified that to 1 part in 10,000. We've also seen that the light, when it goes past one neutron star, bends. And we can see the bending of that light. This is the prediction, is the curve, and the blue dots are our data. And then finally, when the neutron star is going past, or when one of the neutron stars is going past the other, it has this opaque region which blocks the light. So we're effectively shining the light of one neutron star through the magnetosphere of the other one, and that causes the signal to be blocked twice per rotation period of this slow pulsar. And in fact, this pulsar, this is how fast it rotates in real life. And so you'd expect to see light sneak past this disk, then get blocked, then sneak past, then get blocked, then sneak past, etc. And indeed, when the neutron star is right near it, the light should be blocked more or less continually. And so we can actually compare that with our data. And that's what we're doing here. The black is the intensity of the pulsar. And you can see it starts to get eclipsed, a bit more, a bit more, a bit more. And the gap between these pulses is exactly twice the rotation period of that slow pulsar. And we can actually use this to show that the spin axis of the pulsar is changing with time in the way that Einstein predicted. And then in our last experiment, we're using MeerKAT to try and search for the signatures of supermassive black holes that are merging in the universe. If you have two black holes traveling around each other, space and time is compressing our whole galaxy, not by very much, only by 100 meters or so. And if you monitor a whole bunch of pulsars in the sky from the Earth, then when the gravitational waves travel through, you should get correlated delays between the neutron stars. So this is the prediction of Einstein if you monitor how correlated the arrival times are from the different neutron stars. These are recent data from other telescopes that show that maybe it's there, maybe it isn't. And then this is the data from MeerKAT, which is a beautiful confirmation of this theory. And now I do have one last bonus thing, if I've got time. MeerKAT discovered, by looking at this globular cluster, a neutron star right in the middle of it. And it was quite an interesting system. It was traveling around in an elliptical orbit. This is the spin period of the neutron star measured on just a few occasions. And this is our model, which is an eccentric orbit. So there was a neutron star around something which is kind of heavy. And we could use the rate at which the orbit was processing to weigh the system. Turns out it's 3.9 times the mass of the sun for the two objects together. But the pulsar was rotating very, very quickly, only every 5 milliseconds. And normally they only occur in circular orbits. But because of stellar collisions in these globular clusters, you can perturb orbits. And so what we think happened was that there was a white dwarf and a neutron star happily minding their own business. And then a black hole came along, interacted with the system, and temporarily the neutron star was ejected, and the black hole and the white dwarf went into an orbit. But then this didn't quite have the escape velocity, so it started tugging on the black hole and the white dwarf, and they fell back to each other. So we can see that here. Sorry about the flashes. And what's going to happen is going to temporarily go into a triple system, and then the white dwarf gets ejected, and you end up with a neutron star and a black hole going around each other in an eccentric orbit. And so that's what we were seeing. Oh, sorry about the flashing. Back here, this is an eccentric orbit with a neutron star and something very heavy, which is either a very heavy neutron star or a black hole. We can't quite tell. And this was published in Science this year. So my conclusion is that these modern observatories are giving us new ways to test Einstein's universe, and I hope I've been able to explain that to you in a way that you can understand. Thank you.
Thank you very much for this fascinating virtual tour of our universe. Thank you very much, from the very beginnings to the current actual research. Are there questions for Professor Bales? Please.
I have two questions. One is the very basic one, just Hamilton's and Dunn's curve, which you have a large positive correlation at 0 separation and 180 also maximum, but they're not the same value, and it's a bit lower at 180 degrees. So what's the reason of this?
So you want to know the shape of this curve?
And there at 180 degrees, that is a lower correlation than 0 degrees.
Yeah, there's a formula in a paper I can point you at which explains the shape of this, but I can't derive it. I'm sorry.
But physically, I mean, if it's really a quadruple.
Yeah, you get more correlation when you're pointing at the pulsar than behind it.
And the other question is because you only have this bias of more pulsars around the solar system than the other side of the Milky Way. Therefore, the model of your electron density from dispersion relation to the Milky Way would be a little bit biased towards the because you have a kind of asymmetric distribution of the samples. Then when you use FRB, discover FRB and use FRB to decompose at the Milky Way, then there could be also some bias of the DM of Milky Way, because you have this sort of asymmetric distribution of the pulsars in our Milky Way, isn't it?
Yeah, so the color of the stars represents their dispersion measure. So red is low dispersion measure and blue is high. And it's certainly true that our model of the nearby solar system is very good. And the model on the other side is really bad, because we can measure the parallax of these nearby guys and get them quite accurately. And on the other side, it's a bit of a guess. But what's also true is that off the plane, everybody's red. And that's because there aren't many electrons. So we actually know the Z distribution of the electrons quite well, and most FRBs are off the plane. So I'm not too worried about that.
Question over there.
Thank you for this fantastic journey and very nice explanations. I think you used the word quantum exactly 0 times in your talk.
You're a quantum physicist, I take.
Well, I'm a physicist.
Right.
I'm a statistical physicist, actually. I wonder, are there any observations that could necessitate a quantum explanation? Or more generally, when people say that they go beyond general relativity, are there observations that would necessitate that effort?
Yeah, there's certainly no observations that help the fact that quantum theory and GR are not very compatible on all scales. But we are very interested in the internal structure of neutron stars. And the maximum mass of a neutron star depends how squishy neutron stars are. And so my area of research contributes to that by finding the heaviest neutron stars possible. The heaviest ones we know of are around about 2.1 solar masses. And the equation of state of nuclear matter can be informed by measuring both the radius and the mass of neutron stars. And only a few weeks ago, we published a paper jointly with the NITheCS mission, where they used X-rays from a neutron star to model the hotspots and try and determine the radius. And we measured the mass of the neutron star from that time delay. And those papers, that's one of the first times we've had a radius and a mass of a neutron star determined.
I had a question about, what sorts of neutron stars, I mean, pulsars are useful or the most useful for testing general relativity, because I guess there are also these, sort of like earthquakes, or I don't know what you call them, where
Call them glitches.
yeah, the rotation rate sort of changes. And are there other sort of interactions like spin orbit that can sort of change the rotation of a pulsar? Or maybe you could explain how that works.
Yeah, we've done quite a lot of experiments in this area. So the beam of a pulsar, we think, always shines to the same part of the sky unless the spin axis is precessing. And we don't think they do free precession, but if they're in a binary system, the spin axis and the angular momentum axis of the binary couple. And if they're not aligned, that actually changes the direction that the emission cone is transmitting to. And so in the very relativistic pulsars, see that the pulse shape is changing in a secular way over the course of decades. And in fact, in what was once called the double pulsar, one of the pulsars has now completely disappeared and we can't see it anymore, because about every 80 years, they complete one precession cycle. I can't remember what the other question was. Oh, and then there's another system which has a white dwarf and a neutron star going around each other. the white dwarf is spinning so fast that the whole orbit is being frame dragged, and that's causing the orbital plane to apparently change site. And that was a paper in about 2021 that our group published.
I just want to revoke the question that gentleman you asked about quantum. Sorry, do you mind? Yeah. So the one thing is, I think there was some paper talking about the black hole and pulsar binary system, and if the pulsar shedding some light towards a black hole, and there was some theory that around the black hole, then there is some quantum effect and so on. Then if they destruct the interference of the pulsar's light, then there's some quantum structure around the black hole. There was this, what do you call it, firewall paradox and so on. Would you think that be a regime of testing quantum physics via this pulsar?
I mean,
Whaley Penn and Avery Broderick, they have some paper on this.
yeah, sorry, I'm not familiar with that. And I think information paradox and things like that are what they do in Cambridge, but I'm in the real world.
Are there any other questions? Please. And in the meantime, are there any questions from our online audience? Yes? Okay, we will come to that just now. Please be patient.
Thanks for the talk. So, since the first pulsar that Jocelyn Bell discovered until now, we've found many more interesting systems that you've described with, different spins and periods. Are there any tests of general relativity or any other interesting physics that we are still waiting for a pulsar with the right properties to test, especially once we have higher sensitivity telescopes that we can discover more? Is there anything exciting still to look forward to in terms of these types of tests?
Yeah, a pulsar going around Sagittarius A star would be amazing, because you can measure things so much more accurately than you can with normal stars. So that's actually the subject of dedicated observing campaigns with MeerKAT. It turns out that the supermassive black hole was so hot that our telescopes aren't actually that sensitive when we look at it with low frequencies, and so you want to use higher frequencies. So our friends at the Max Planck Institute have actually built a very expensive system to take like 4 hours of MeerKAT data, a baseband from every telescope, and really carefully try and search for a pulsar. Also, just having a pulsar going around a black hole where the system is edge on, you'd be able to see interesting frame dragging and things like that. But unfortunately, the system we discovered, if it is a black hole companion, and we can't tell, it's either the sort of heaviest neutron star or lightest black hole, we're not really sure. It's actually quite face on, and so it's very hard to measure these effects. We want to get an edge on one.
Okay, great, thanks.
Okay, let's move to the questions from the online audience. I think the microphone is on the way.
There was one question about dark matter and dark energy. Would it influence these predictions or not really?
Yeah, so although dark matter dominates the kinematics of the galaxy, its actual density is very, very low. So its effect on these type of tests is almost inconsequential. There are some theories of dark matter that dark matter could somehow be captured by neutron stars. I think that's probably unlikely, but it keeps us in a job, I guess.
Are there any more questions from the online audience? Then it's my pleasant duty to thank you very much for this fascinating talk and to offer you a magazine that NITheCS publishes to encourage high school kids to get interested in science, technology, and mathematics. Yeah, so thank you very much.
Oh, thank you.